And I'll say today's speaker is Dr. Tristan Petit. He did his dissertation work in diamond color centers, diamond physics. And subsequent to that was young investigator group leader, junior research group leader, and now I believe is I've lost the description. Your title is again now?
It's still a young investigator group leader.
Young investigator group leader at Helmholtz-Zentrum in Berlin. And with that, Dr. Petit, we're looking forward to your seminar.
Thank you very much. And thanks for the kind introduction. I'll talk today about soft X-ray spectroscopy, and especially how to look at solid-liquid interfaces and nano-interfaces. So I'll explain a bit what that means. So we know about interface. So this is basically the surface that will separate two phases of matter. And the phase can be either a solid, in this case, and a liquid. So this is the interface I will talk about today. And they play a major role in a lot of applications. So the topics which are of interest for us in AGP are, for example, photovoltaics. So you have a lot of layers and how charge are transferred at all this interface will drive how efficient is your solar panel, for example. In batteries, this is a true solid liquid interface. So we have an electrolyte interacting with an anode and a cathode, and a lot of processes are happening at these interfaces. So we try to understand with spectroscopy what's happening at this interface. And what I will focus on today is actually what we call also nano-interface. So this is an interface between two phases, and one of which is nanomaterials. So that has a big influence on the effect we will be looking at, because for a bulk interface, basically you have to really zoom in very close to see the region where the properties of the material is different from the bulk. So this is usually a region which is a few nanometer big. So if you have a solid state, this is not so easy to access. But when you have a nanomaterial, then this interfacial area becomes very important and brings a lot of new properties to the material. So basically, you can either have a nanostructured interface. So in that case, we have this kind of structure where both the solid and the liquid have a high surface area. We can also have colloidal interface, and where nanoparticle will be dispersed in liquid. And in that case, only the nanoparticle has a nanoscopic characteristic length, and the liquid is a classical solution. We have also nanoporous interfaces. So in this case, the pores have nanoscopic scale, and the material itself can be a bulk solid. And then we also have nano-layered interface. So in this case, both so it's typically layered materials with 2D materials, which can be very thin. In this case, it's only interface from both the solid and the liquid phase. And I will show you today some examples of spectroscopy on these different techniques. But first, I want just to give you some example of how they look like in real life. So I will start with nanostructured interface. So this is typically a surface you use for anti-fouling or super hydrophobic surfaces. Basically looks like a lot of tips like this, and air bubbles or bacteria cannot adhere to the surface. So this is something which has been used for many applications. For colloidal nanointerface, so basically colloids and nanoparticles are used for many applications, and something which is changing when you compare to the bulk structure is, especially the solvent will restructure at the surface of these nanoparticles. So there have been some work using X-ray diffraction. I think this is from ESRF, where they looked at pair distribution function and looked at solvents change on the surface. But this is from structural characterization. We will see today how it looks like from the spectroscopy side. And this kind of restructuration will impact how the particle interact with the environment, for example, in cells. It will also affect the surface charge and tune their properties. So it's quite important to look at this hydrogen shell on nanoparticles. So with mesoporous carbon, there have been a lot of work today to try to make chemical reaction in this kind of nanoporous reactor. So we have very confined environment where the solvent may have different properties and may trigger faster reaction, for example. So this is something which has been called also nanoreactor, for example. Looks very exciting And last but not least, nano-layered interfaces are especially very interesting for energy storage application. So there is a typical material where we will intercalate cations and they will de-intercalate. So this will how you can do some capacitors or battery type charging. And there is a lot of research at the moment trying to understand how this intercalation process works, because it depends, of course, on the properties of the active material, which will be our solid phase, but also on the electrolyte, which will be our liquid phase in such interfaces. So yeah, this is the topics I will talk about today. So I think the community following this series knows about X-ray absorption. I'm particularly interested in the soft X-ray because we have, of course, we keep the high elemental specificity, but especially for light elements. So I will talk today a lot about liquid aqueous interfaces. So we look definitely at oxygen from the water, but we can also look at LH of transition metals, of first order transition metals, and MH of second, and even some of the third order transition metals. And another thing which is very important, that soft X-ray is very sensitive to local chemistry. So I like this example from theoretical calculation showing an eta group on the carbon quantum dots. I don't know how you could call that. And if you compute the X-ray absorption from the carbon linked to the oxygen, you will have an absorption peak around 287 eV, for example. If you go one bond further, you will have a very strong chemical shift. You see the peak shift around 284. And then if you go at a second bond longer or 3 bonds, then actually the signature will be exactly the same. So basically, it shows that we basically have a sensitivity up to 2 chemical bonds. So we are looking at very close changes of electronic structure, close to a defect in this case. So another thing which is very interesting, especially looking at aqueous interfaces, is that it's very sensitive to hydrogen bonding. So these are 3 examples of water molecules. So if you take water molecules in the gas phase, you will have these very definite orbitals that will broaden a lot when you look at the liquid phase because of the hydrogen bonding between the water molecules that will change the charge distribution around the oxygen atoms. And between a liquid and an ice phase, you see that we have very strong changes of the electronic signature of the oxygen KH. And this is something we are using to look at water phases in our nanomaterials. So that's about why we're interested in X-ray absorption spectroscopy. And something I need to discuss a bit more now is X-ray attenuation length. That is very important to take into account when we look at nanostructure. So basically, can define first the volume that will be probed by our X-ray excitation. So this will depend obviously on the energy of the photons, and basically we will illuminate a certain volume of the sample. And then depending on the techniques we use to detect the X-ray absorption, we will probe either the same volume or a smaller volume. For example, if we look at electrons, and this can give our probing depth. So either very surface sensitive if we look at electron, a bit deeper if we look at photons. And something which is important is that if we look at nanostructured surface, it turns out that we start looking even with surface sensitive techniques, we can actually probe all the nano particles that so in this case, nanostructured surface that we're looking at, all the nanostructure will be actually probed by X-ray spectroscopy. So if the attenuation length is in the same order as the nanostructure we are looking at. So just to give you an idea of how long is this attenuation length in the soft X-ray. So this is for X-ray photons. So typically, if we look at a material in water, the water will absorb a lot as oxygen KH, obviously. So if we are looking below the oxygen KH, we can actually have X-ray penetrating up to 10 microns. And above the oxygen KH, and this will be strongly absorbing. So we are actually looking at below 1 micron. So if you have strongly absorbing material, we are probing in a few tens, hundreds of nanometer. So this sounds, 10 microns sounds a lot, 100 nanometers sounds not so much, but actually compared to electron, then we are 1 order of magnitude smaller. So the attenuation length is more in the order of 1 to 10 nanometer. And this, of course, depends for the X-ray photon on the photon energy. for the electron on the kinetic energy of the electrons, but I will not spend much more time on that now. So based on this consideration, there have been different techniques to actually measure X-ray absorption at solid liquid interface. So the first thing is the transmission measurement. So basically, you just try to have a volume thin enough so that the X-ray doesn't get fully absorbed by your layer. And then for solid liquid interface, there are two cases. So I'm taking here an example of nanoparticles in solution. So either you, let's say we have a carbon nanoparticle. If the nanoparticle is absorbing in transmission, you will probe the full volume of these nanoparticles. If you're looking at the electrolyte in this case, so where the second phase will be absorbing, so the oxygen, then you will probe the full volume of your electrolyte. So this is kind of bulk sensitive measurement. The problem, of course, is that we need to have some technology to make these layers extremely thin. So I told you before, below 10 micron, depending on the absorbing element, can be even below 100 nanometer. So that's why there's been a lot of work in fluorescence yield. So in this case, we excite our material with an X-ray photon, and we also detect X-ray emitted photon. So photon in, photon out technique. So this has the advantage that we can have much larger liquid cell. And in that case, basically the probe volume will depend on how deep the X-ray photon are penetrating. So if we take again this carbon nanoparticle, so it might be fully absorbing if it's very close for the interface. If it's further away, we might not fully image these carbon nanoparticles. And if we look at the electrolyte, basically it will be progressively absorbed in the liquid, so you will not see electrolyte very far away from the membrane, and you will have a high detection from what comes here. So another technique is electron yield. So this is something we know from vacuum measurement, that we get electron emitted from the surface. So in vacuum, it's easy to get electron out. But there have been also some groups developing electron yield in liquid recently. So this is a bit more complicated. So you need some lock-in detection to be sure you're detecting electrons only emitted by the X-ray. But this is very interesting because you can actually start looking at surface effect in the nanoparticles. So in this case, we are looking at electrons. They will be only emitted from the first few nanometer of the nanoparticles. And if they manage to reach the membrane, which is usually coated by metal film, then you can actually look at interfacial processes and interfacial water layers near these interfaces. And a second process, which is called ion yield, is kind of a similar process, but instead of looking at the electrons, we are looking at secondary processes like ions, which will be formed from the decay process of the electron in solution. So in this case, we just have a counter electron in the electrochemical cell that will detect the current, and this current has been found to be proportional to the X-ray absorption. So in that case, we are probing deeper in the solution, the same as what you do with fluorescence yield, but you are probing only from the region that can emit electrons in the nanoparticles. So these are just to show you that there are a lot of different techniques to detect different kind of signal, interfacial signal in liquid. And yeah, that's why I showed diagrams, because the real cell is much more complicated. I will not enter into details, but basically it's, yeah, there've been a lot of engineering to try to transfer these processes to real cells. So I just want to spend a bit more time on what we're actually doing in my group. So we currently work a lot using scanning transmission X-ray microscopy, which is basically using a transmission cell, but instead of just looking at the full X-ray absorption over a full volume, we actually focus the X-ray beam here, and then we can scan our cell under the X-ray beam and then get both this spectral information from X-ray absorption, but also spatial resolution. So this is yeah, how the X-ray microscope looks like in BC. This is a new Mystic beam line that will come again later, and it's actually open for user, someone interested in this crowd. And basically this reach energy from 250 to 1500 eV. And we've been developing different cells to be used in this microscope. So we have one cell for high temperature, up to 1000 degree in vacuum. We have a cell for heating the sample in a gas atmosphere. And we can develop also this transmission measurement directly in this solution. And we also have an electrochemical cell where we can look at these solid-liquid interfaces directly in solution. So something that's important, so I mentioned this is a transmission X-ray microscope. So this is mainly measuring in transmission, but especially if you work in vacuum, you can also use these techniques with electron yield. I will show you an example later, and even with fluorescent yield. So some people have been developing that in other synchrotrons. So with that would be my first question break. Is there any?
I don't see any questions, so I think you should continue.
Perfect.
Okay.
So I will start with showing you some examples of our previous work on nanocolloidal interfaces. So in this case, we are looking at nanoparticles dispersed in a bulk liquid. And I'll start with nanodiamonds. So I've been working in nanodiamonds during my PhD. And basically, these are very tiny crystallite of diamond, so which are around something like a few nanometer, between, let's say, 3 and 8 nanometer. And has a crystalline inner core, and the surface is a bit more amorphous. And these nanoparticles form very good colloids that can be stable in solution. And we've been able to measure carbon X-ray absorption spectroscopy directly in a liquid solution. So for that, we've used transmission measurement. So transmission at the carbon edge is a bit tricky because we have to have a very, very thin layer. But this was possible. And then we've looked at different kind of nanoparticles. And basically, you can see that in this region here, we see different bands that I will not enter into details. But basically, here we see different features which are classical for a diamond material. What I want to stress more is that if we measure in fluorescent yield, especially in this case, we used a microjet. So this time we don't need to have a liquid sample which is so thin that we get X-rays through. So in this case, the microjet will be a liquid phase, will form a liquid phase in a vacuum. And typically the diameter of such microjet is around 50 micron. So the X-ray doesn't penetrate through, but in fluorescence, we don't need that. And the good thing is that when we don't have any membranes between our electrolyte and the vacuum, so we directly have the liquid in the vacuum. And when we looked at nanodiamonds, either in vacuums or deposited on a substrate or in liquid, we actually saw very different processes. So if we look especially in the pre-edge region, so we are looking in this region in more details here. We saw that on a particle which has been in vacuum, we actually have pi star transition from sp2 carbon. So this comes from partly graphitized structure on the surface. But we found out that this peak actually disappear in solution. So they probably form a different chemical structure by interacting with a water molecule. And we know that these pi star transitions are only on the surface, are not present in the bulk, which is sp3 hybridized. And on the other hand, we saw an appearance of another band at lower energy that actually turns out that this is at the pre-edge of the X-ray emission spectroscopy. So it's actually at the beginning of the valence band, and this was interpreted as really hole formed due to a charge transfer, for example, with some water molecule in the surface of the nanoparticle. So the good thing here, we really benefited from the element sensitivity of X-ray to the carbon, and we don't have any signal from the oxygen itself because it's absorbing at higher energy. So this is what we got from the carbon edge. But what was also very interesting is to look at the oxygen. So then we are looking at the water itself and not the nanoparticle directly. But if we compare to, so this is transmission measurement. If you compare to a pure water spectrum, so in blue, you have a pure water spectrum. You remember I told you due to the hydrogen bonding, these bands are being broadened. And when we increase the concentration of nanodiamonds in this solution, we basically saw that this absorption coefficient went much higher. But the pre-edge was not changing much. So this is basically showing that the hydrogen bonding was changing a lot. And especially we are increasing the absorption in this high energy region, which corresponds to strongly hydrogen bonded structure. So we kind of have a more structured water when we increase the concentration of nanodiamonds. And this is also something which have been also visible, for example, by the density of the liquid that becomes kind of a gel at this very high concentration of 8 to 9%. Something which was very interesting also is that if you compare these changes to what has been measured before with salts, we actually saw that the changes with nanoparticles is much, much larger than what has been found on salts. So if we convert 6 molar is around 35 weight%, so we are way higher concentration than what we have with nanodiamonds, but you can see the change are much, much smaller than what we observed. And this is due to the fact that around an ion, we'll have a surface shell, which is most likely 1 or 2 water layers, while around these nanoparticles, we may have restructuration, but much longer range. And this depends on the surface chemistry of the nanoparticle. So this was an example with colloids. Now I want to show you an example with a nanoporous material. So in this case, we worked with some colleagues now in Jena, so the group of Martin Oschatz, where they produce mesoporous carbon, basically by carbonizing a precursor, which has a lot of nitrogen. And by changing the temperature of this condensation process, they can tune either the crystallinity, the carbon crystallinity of the material, and the nitrogen content. So basically here, you can see that nitrogen is around 30% at the lowest temperature and goes down to 5% at the highest temperature. And on the other hand, I didn't show you that, but at 1000 degrees, you have a very graphitized structure, while at 550, it's still a bit more amorphous. What is interesting is that you can see that these particles are a few micrometer large, and they are rather thin, so they look like small platelets inside. And these are very good sample for X-ray microscopy. So in this experiment, we actually used a cell developed by Jan David Förster, who basically had the sample can be squeezed between 2 silicon nitride window, and we can flow a gas, and especially in this case, humid air, to change the humidity in the cell and look at how the water condensate in this mesoporous carbon. So this measurement has been done in a stick SEM I showed you earlier. And basically, we can look at single particles here. So you see it's something like 10 microns large. And we record the X-ray absorption spectra through this particle with special resolution. So especially, we could distinguish a core and the surface area. So basically, in the core, the X-ray absorption will be kind of saturated, especially at the carbon. So you can see here in solid line, the surface area, and in dark line, the core. And basically, I won't spend too much time, but you can just see the core is kind of saturated while you see spectral features coming from the surface. And we compared like 3 different temperatures. And this is what you see at a higher temperature. We have a stronger component, C1, around 284.5, which is mostly graphitic carbon. While for the other samples, we have peaks, especially situ here, around 285, 286, which is related to CN bonds. And this is confirmed by the nitrogen KH, where we also see 2 kinds of nitrogen. So CN in the pyridine structure and CN triple bonds. But I want to spend a bit more time in what we observed at the oxygen KH. So oxygen KH is not coming from our material. It has quite low oxygen content, but it's due to its nitrogen content, it's very hydrophilic, so it catches water very efficiently. And what is interesting is that we could extract different signature from the oxygen inside the core of the particle and in the surface area. So especially here, if you look at the lowest temperature, you can see that we have these sharp bands in the core, while in the surface, we start having a bit more structure at higher wave number. So again, this region is related to strongly hydrogen bonded water, while here it's lowest, water molecules which are not hydrogen bonded. And the O1 is actually the oxide layer coming from the material itself. So that's also another example where the strength of the X-ray absorption is that we can separate the oxygen that comes from the material itself from the water. So this is what happened at 550. At 700 degrees, we observed a bit the similar structure with a bit more water on the surface, but this may also come from the different shape of the particle. So this is, of course, what happens with microscopy. But what was very interesting is that the 1000 degree sample, which has very low nitrogen content, has a quite different signature. So basically, we could see that the water was much more structured inside, but also in the surface area. So this measurement had been performed at low humidity. And basically, this was a good example where you see that microscopy is actually very interesting to differentiate different structures that we would not be seeing if we just average over the full particle. The next step was then to change the humidity in the cell. So here I just label it low, medium, and high. So medium is typically around 30% of humidity, and the high temperature like 70%, if I remember well. And basically what we observed is that on the surface of the particle, we would have the buildup of water layer that is very close to a liquid water. And this was observed for all the three particles. And it was saturating a bit faster in this most carbonized sample. And in the core, we did see a bit of increase of the signal, but you see that it doesn't form a very liquid-like water inside the pore. So this shows that even if we have very high humidity, either the water cannot penetrate inside the inner core of the particle, or the pores are so tiny in this area that they actually cannot form extended hydrogen bonding network as in a liquid phase. So this is the first measurement that have been done on this kind of mesoporous carbon. And this was very exciting to see that we observed the different water phases in this environment. So I have my second spot for questions. I also drink some water.
Okay. Peter, would you like to ask your question?
Yeah, can you hear me?
Yeah.
Yes.
Yes, thank you for very nice, very interesting talk. I was wondering these experiments on the mesoporous carbon. You did this at high temperatures?
No, we did it at room temperature.
Okay. Because I was a bit confused with the numbers you put in then 700, 550.
Yeah, okay. Now the 700 and 1000, this was the temperature used for the synthesis. So basically, it was the temperature used to carbonize a particle. And then when it cools down, then it just keeps the structure. So
okay.
And then the measurement was just at room temperature in all the cases. Yeah.
Do you know the pore size of the carbon materials?
Yes, so there are different pore size ranging around, so most of the pores are around 5-6 nanometer, I believe. And then we do see some bigger pores like 100 nanometer that were basically probably from the surface. But I don't have the curve here, but basically you can find it in the paper that was cited.
Yeah, because it of course you interpreted it now, right? Based on the fact that, okay, some of the water are outside and why some are inside. But of course, sometimes even the water, you can experience a huge depression of the melting point or freezing point because it's confined. So it could actually be that you actually have water that is in different states, not really just about the confinement, but basically because it might be in a different state. In this case, do you check about this? Because if it's really very, very small pores, you can actually find out that you can actually change the even a freezing point of water, and then you might actually have something that is different, maybe ice and then water. Or So did you check?
So definitely, I mean, what we just checked is that the temperature was constant, so the temperature of the cell was constant. But obviously, if we have a different phase, it means that it could be like an ice phase that is stable at room temperature. So it might be that, if we would hit at 200 degrees, that maybe this would disappear.
Yeah, exactly.
Definitely. So
I
agree with you.
Yeah. Okay, thank you very much.
But maybe just to stress that the signature we have here is actually not a gas phase. So it looks still different from a gas phase, and it looks different from a liquid. So it's kind of in between. So probably the molecule is blocked in some configuration. It doesn't rotate as much as a gas phase molecule, but it keeps still some features that is from water, which is kind of isolated from other water molecules.
And if you look at the nitrogen, because it's nitrogen-doped carbon, do you see also any possible interaction between the water and the nitrogen in this case?
Yes and no. So we didn't see it with X-ray microscopy because the pixel size here is like 30 nanometer. So when we probe with the bulk phase, we mostly see the nitrogen which is not in contact with water. But we also did ambient pressure XPS measurement. So in this case, we probe only the first nanometer, and with ambient pressure XPS, we actually did see some change of the nitrogen with water. But yeah, we're still working on this data.
Okay, thank you very much.
Yeah, we should move on to the next question. That was outstanding. Olivia, you have a question, please?
Yeah, this is really cool work. Thanks for sharing it. I was just curious as to what kind of stuff you do at Bessie, or I guess at Mystic, to correct for higher order light, or if you do anything extra to account for like carbon contamination in your beamline when you're doing these carbon experiments.
So the good thing with X-ray microscopy is that actually we are measuring the background at the same time. So we do have some carbon contamination, obviously. But if you look at the area, for example, here, which is free from the particle, this is what we use for our baseline. So we're actually measuring the I0 at the same time as we measure our sample. And the spectra are corrected from areas of the silicon nitride that doesn't contain carbon. So in this signal, we have the correction from the carbon beamline contamination.
Cool. Do you use like a titanium filter or like a nitrogen chamber to grab some of the higher order light, or do you not find that's a problem with some of your measurements?
Actually, so in our case, so with the STIXM, we actually focus the X-ray with a zone plate. All the higher order line is actually filtered out with this element. So we have a stopper for the zero order light, and then just the X-ray that fits to the right harmonic actually focused on the sample. We have less problems than standard X-ray absorption, I would say. So that'd be nice.
All right, cool. Thanks so much.
Welcome.
I'll ask a question, Tristan, while we wait to see if there's other questions coming. So you had that wonderful slide that showed the difference between the structure for the confined water and the bulk water.
Mm-hmm.
And you don't have to go back. Sure, this is good. And you also had a slide which showed the much larger effect of the nanodiamond on structuring the water as opposed to nanoporous or mesoporous, or as opposed to a sodium chloride solution. Yes, that was slide 17 or thereabouts. Okay. What's interesting is my group's just been doing something in kind of the overlap of those two results, which is we've been looking at contact ion pairing in bulk solution and in nano-confined solution.
Oh, sounds like it's interesting.
And yeah, and we're finding that there has to be something very different about the water in order to explain that there's enhanced ion pairing in the nano-confined space. And so your Wu et al. Paper in preparation, please hurry up and submit it. We're waiting for you to give us the physics we need to explain what we see.
Great, yeah, it's almost ready.
Yeah, we have one last question from Cas4. Sorry, I don't have a name. I apologize.
Yeah, I was just curious. Could you clarify the difference between the 6 molar sodium chloride and the surfaces? Were you trying to say that there are more dangling hydrogen bonds, or that it's longer range?
So if I just come back quickly. So basically, what was happening in the sodium chloride is that we have some enhancement of these two first bonds and the decrease of this one. So basically, we kind of destroy a bit hydrogen bonding, and we have more of the poorly connected water in the solution. So it creates more, it's more like a chaotropic behavior. In the diamond, this was the opposite. So we have no change in this region here, and we do have a very strong increase in this, like more in this range. So especially this post edge is also increased, which is something which didn't happen with the electrolyte here. But I would say this would be the biggest change.
Thanks.
You should please continue.
Yep. So I will continue then with a nano-layered interface, which is very exciting. Especially we're working now a lot with a material which is called MAXene. So it's a transition metal carbide, which has a quite nice structure because it has, this is an example with titanium-3 situ. So we have 2 layers of carbon, 3 layers of titanium, and a surface chemistry that will interact with an electrolyte. So basically, process is for chemists. What is interesting is that you have this layered structure where you basically have kind of this is our solid phases. And between this confined layer, we will do we can have some electrolyte entering, and both the atoms here are in a nano-layered, but the electrolyte is also kind of in a nano-layered phase. And this is again a material that we looked with X-ray microscopy. So maybe here you can see the stopper that stop this high order light, and then the X-ray will be focused on our Maxine sample, and then we can scan our particle and look at either the transmitted signal. So this is a stick SEM that we just saw for the mesoporous carbon. But in this case, we also look at the drain current on the sample holder. So we can also record electron yield at the same time. So this is a very nice example where you can see 2D materials both in the bulk and on the top surface of our material. So if we go a bit more detail, so this is a typical example of some overlapping Maxine layers. And what you'd see, or don't really see maybe, that here we have a monolayer. Sometimes the absorption is very small. So here these are 2 monolayers. So this one is a bit shifted because there is some background below. And then basically the absorption will increase by the number of layers. And we can determine that the blue area is a 4-layer material, and this is a 5-layer material. So this is measured with the titanium LH. So we look here at the titanium inside these layers, but the absorption we get is actually from 5 times 3 atomic layers of titanium. So this is something which is interesting. And so for now, this is in vacuum, but imagine that if we put this in an electrolyte, so 2 out of these 3 titanium atoms will actually be interacting with an electrolyte solution. So this is what you see in transmission. So you see different thicknesses. And what is interesting is that when we observe the same particle simultaneously with electron yield, in that case, you see that it looks much more homogeneous. And this is because we're actually only detecting signal from the top layer. So if it's 5 or 1 layer, it doesn't change so much the response because it's mostly depending on how the electrons are being emitted from the sample. And something which was very interesting was just by chance that we saw that actually, but if you compare these 2 layers, which are actually monolayered, determined from the transmission measurement, you can see that one appears very dark and one is much lighter. And this is just because for some reason, there is another element that breaks a bit the contact between this particle and the other, so we have much less electron emission from this particle. So this is just a nice example to show you that we can look at these 2D materials, and basically by changing the detection mode, we can learn different information on the material. Of course, talk of today is about solid-liquid interfaces. So we are developing an electrochemical cell that you can see here. So wait, I have the cursor on the wrong screen. Okay, that you can see here. So this is the same beamline, the X-ray microscope at MISTIC. And basically, you have a cell where the liquid can come in and out. And in between, we are squeezing our liquid interface between 2 silicon nitride. I explained you that before already for non-microscopic cases. But what we can do here is deposit our Maxine particles or our layered materials directly on an electrode here that will be exposed to the X-ray. And then by scanning, we can look at this single particle in solution. And of course, I told you this is material that we use for energy storage applications. So we want to charge and discharge it at some point. So that's why we have some contacts to use it. So this is actually a figure from Lim et al., which did this kind of measurement on battery particles, so lithium iron phosphate particle. But this cell has this kind of design has been used for many other applications, and we use it for looking at Maxine. So basically, this is how it looks like in real. So we have our 2D materials, layered materials, that is deposited on a gold working electrode. This is the gold electrode. And here we see the window border. So the bottom electrode is here, and then the top electrode is here. And basically, if we see through the silicon nitride, then we mostly have our particle absorbing. So this is at the titanium LH. And you can see that we have some particles which are very poor contrast. So this is maybe 1 or 2 layers, and some which are much larger, which may be like 20 or 30 layers thick. So we've run this cell quite stable for several hours. And basically, this is a Maxine particle. The image is just by changing the energy. So you can see if we get away from the titanium LH, it is not absorbing anymore. And when we are on the titanium, it absorbs a lot. So this is clearly a titanium carbide particle. So in this case, the water thickness in the cell is around 10 micron. And what we've been trying is to look at the response of the titanium by different electrolytes. So we started with acidic electrolyte and then changed it to lithium chloride. So one thing you can see is that half of the particles were washed away when we change the electrolyte. So this is the experimental part, which is not so nice. But the nice part is that some of the particles were actually there in both cases. And if you compare the absorption spectra, we could see that the particle measured in sulfuric acid are very different signatures than the one in this lithium chloride solution. And this is mainly due to change of surface chemistry. So in sulfuric acid, we do have a protonation of the surface that will lead to titanium in a lower oxidation state than in this lithium chloride solution, where the surface of the MXene is much more oxidized. And since 2 out of 3 of the titanium are changed, we are mostly sensitive to this titanium that is impacted by the electrolyte. So this is a very nice example of what we could see here. And what I really loved about the microscopy is that we can also look at the sub-particle level. So if we look at inside and decrease the pixel size, so in that case, we didn't measure full spectra, but just a few points, then you can extract some area which are actually more oxidized than others. And especially in this lithium chloride solution, it looks like the center of the particle were much more oxidized than the surface. So this is what happens when we look at the titanium. In another experiment, we actually also looked at the water layer in this confined environment. So in this case, in vacuum, and we cooled the surface so that the water stay trapped in the particle. And basically at very low temperature, so this is 220 Kelvin. In this case, this was photoemission microscopy, it was not 6M anymore. But what you could see is that at low temperature, we mostly see 2 peaks which are coming from the oxide layer on the MXene. So this is the oxygen, T2G and EG. So basically the different kind of oxygen bonded on the surface. And as we heat the surface, we actually see some bands appearing here that actually are related to the water in this confined layer. So here I bring back this picture from the beginning. You can see that if we extract the background from our MXene layer, this is the signal that we obtain from this nano-confined water. So we are not talking about mesoporous, we are talking about water confined in between 2D planes. But we also see that we have kind of mixture between the gas phase. We see these very sharp lines, 533, 535 eV, that looks close at this one, but shifted in energy. But we also see like higher peak at higher energy that is related to more hydrogen bonded water. So this is another example that water can have different phases in confined environments. So with that, I think, do I have still time to show some example on this, or I should jump on the conclusion?
You have 10 minutes, certainly.
Good.
Okay.
So yeah, then I'd show my last examples on the nanostructured interface. So I go back to diamonds. So this time it's not a nanodiamond. This is a wafer of diamond, the polycrystalline diamond. So this is how it looks like, on which we have etched. So actually Peter Nittel, our colleague from the Fraunhofer, did etch some nanostructure on the surface. So it looks like this if you zoom in. And this is a very nice material to look at and to compare basically the sample which has big particle and the nanostructured layer. So we've been comparing this material with oxygen and hydrogen surfaces and compared it to single crystal diamond, also with oxygen and hydrogenated surface. So this diamond is called diamond black because it looks black, and the SC is for single crystal diamond. And what we could observe is that we are looking now in vacuum at carbon KH, and we do see features from diamond. I will focus especially in the pre-edge region. So we have very strong line here related to exciton in the diamond. So we see that it's very strong for very pure single crystal diamond. For this nanostructured diamond, this peak kind of disappear because of the much smaller sizes. And we do have some other bands coming from the surface groups that gets enhanced on the nanostructured surface, especially the oxygen groups. And we also see that some of the hydrogen, of the graphitic structure is increased compared to the hydrogenated diamond surface in solution. Sorry, in vacuum, sorry. So in the next example, actually, I will not talk about X-ray absorption, but ambient pressure XPS. I told you we do also do a bit of ambient pressure XPS. And what is very nice is that in this case, we have our nanostructured surface and we expose it to water vapor, so a few millibar of water, so typically 5 millibar. And we can see that water adsorbs on the surface. So this we monitor by looking at the oxygen 1s. But what I want to show you is especially the carbon 1s, so what happens at the carbon 1s. If we look at the hydrogenated oxidized surface, we basically don't see any difference on the C1s between the sample measured in vacuum and in the ambient pressure of water, irrespective of the excitation energy. So here we are exciting at 600 eV and 1200 eV. But when we look at the hydrogenated surface, which is much more unstable and will react with water, we did see a very strong change in the carbon 1s. So this is basically the dry state, and this is the humid state. And what is very interesting is that if you increase the energy, you see the change is much smaller. And this has to come with the mean free path of the electron. I told you earlier that depending on the kinetic energy, the electron will go deeper or closer to the surface. And this is a typical example where at 300 electron volt, we are very low. So the mean free path is very small. It's around 1 nanometer, while 1,000, so 900 eV, it will be almost double. So we actually probe a very small volume, so less than 1 nanometer at this excitation energy, and we probe much deeper. So we do see much less interaction between the top carbon atom with the water layer. So if we look in more details, the changes, we can also learn chemical information about how the surface has been modified. So typically with XPS, you have a strong peak from sp3 carbon, it's diamond, remember. And then we have the CH group on the surface. So this is a hydrogenated surface, but we also see some hydroxide and CO. And obviously the hydroxide gets more than double after it being exposed to water. And this is really related to reaction with the water on this interfacial region. So at this stage, it's still not fully clear if the reaction is triggered by the X-ray or if this is a spontaneous reaction happening between the diamond and the water. So yeah, this was just a brief example because I wanted to show you some example of this for nano-interfaces. Basically, what I hope I stress is that we have quite different chemical and physical properties that can appear due to the fact that we have nanomaterials, which can be either shown by the fact that surface effects have a much higher change of the material property itself, or that the liquid itself will be changed. So the property of the liquid may change at this confined environment. So soft X-ray is very sensitive to this. Especially we can look at element specificity. I showed you an example with carbon and with titanium for the solid and to oxygen for the liquid phase. And obviously this works very well when the solid and the liquid have different phases. Looking at a carbon particle in an organic electrolyte is much harder. And I also showed you that playing with a detection mode, so using fluorescence, transmission, or electron yield, we can learn different kind of information on our material. I showed you that depending on the kind of water confinement we are looking, so around nanoparticles in confined carbon, porous carbon, or in 2D confined layers, we do see different kind of water phases, which we are still at the beginning of understanding them. And I also show you that in situ STIXM and X-ray microscopy in general, it's very interesting to look at what happens on single particle and when you expect some heterogeneity in the sample. So with that, I'd like to thank my team. So the picture is a bit old, but at least the results I show you are from beans on this mesoporous carbon, from Fedra on the Maxine vacuum, from Pear, and Namrata, which is not on the picture yet, but I think she's around in the crowd, who worked on this electrochemical STIXM cell. And with that, thank you for your attention, and I'm open for any questions.
That's wonderful. Thank you so much. We have a first question from Maria Chan, and other people should be putting their questions into the chat, please.
Thanks. Very nice talk, Tristan. I put the question in the chat, and like 2 minutes later, you mentioned that. I was asking about whether you're also working on interfaces with organic electrolytes, and you said it's much harder. If you want to elaborate.
Yeah.
Have is when you look at batteries, if you have operando studies, are there any issues with the scanning time and beam dosage and so on?
Yes, so I think one of the challenge we have is that the carbon absorb at much lower energies than the oxygen. So at the beginning, I showed you that the oxygen, I think maybe I have actually, yeah, maybe here, I have it here. So basically, when we look at, I showed you this example with titanium LH. So when we look at this titanium in water, we don't have any absorption from the water. So the probing attenuation length is very large. So if we have 10 micron of water, we still see our particle. While in organic electrolyte, it will absorb at carbon. So basically, attenuation length is much, much smaller. It's only lower than 1 micron. So we would have to squeeze our liquid in a volume much, much smaller.
Okay.
And I have my son coming up. J'arrive. Laissez-moi tranquille.
So then it's hard to set up the electrochemical cell that way.
Yeah. That's so some groups have done it. Some groups have done it, but it's much more complicated experimentally because it has to be very small.
Got it. Thanks.
Okay, I'll ask a question. You have these very large spectral changes on confinement of the water, for example, in the colloid and the nanodiamond. And you showed that with soft X-ray. And I'm just curious, would there be benefit to doing similar kinds of measurement with X-ray Raman scattering instead? And so then, of course, you're much more bulk-like, and you have the option of using different selection rules. And I just wanted to pick your brain on that. You're muted.
Yeah, sorry. Yeah, that would be quite interesting. I mean, I know that has been done for ions, so ionic solutions, and that could definitely be interesting to look at diamond, and especially there's been also work at high pressure, for example, which are very hard to do
Yes,
in
soft
vacuum,
X-rays.
soft X-ray. But if you can fit a cell with some pressure, I mean, this could be something really interesting. Yeah.
Okay.
That's a good idea.
All right. Susan Cumberland, do you have a question? Susan, you have a
Hello,
question?
sorry,
Oh,
yeah,
it's
it
okay.
took me a minute to unmute. Yeah, no, I have a very similar question to Jerry about FTIR, which I don't know a lot about the technique, but I know it measures OH and COH and all these types of bonds when you do a RAM, but it would be in the bulk, obviously, and not penetrating through a nanoparticle.
Yeah, so yeah, this is a part of the show I didn't show today, but we actually do a lot of infrared spectroscopy in parallel. And we do see very strong changes of the hydrogen bonding from the infrared too. So this is definitely very complementary. And this is especially interesting in this layered materials. So we do have some very nice work where we do see the change of the solidation of ions, for example, in these layers using infrared. So it's definitely very complementary to what we see with X-ray. So of course, with X-ray, we have the advantage that we can directly compare what happens to the water and to the nanomaterial itself. For the infrared, I mean, it's much harder to differentiate what comes from the particle itself and the water if we look at something else than the OH stretching, for example.
Okay, thank you.
All right, we have time for 2 more questions. Peter and then Adrian, please.
Yeah, so my question is related to the effect of the beam on the electrolyte of if you use liquid, especially water, you can form radicals when you bombard them with X-ray. Do you know what is the effect of this on what you observe actually? Yeah.
Yeah, that's of course something we are trying to be careful about. So this is also one of the reasons why we don't work with organic electrolytes or with water. We don't ionize directly the oxygen level. So we do side balance electron, but it's much lower excitation than what we would have, for example, with electron microscopy. That being said, there are some samples where we do see that they evolve on the beam. So this is not the example I show you today, but we have other examples where we see that the particle is changing on the beam and under special conditions. So we do see in some cases sample damage. But this is also why I'm very interested with the stick SEM technique, because basically the beam stays on the sample, I mean, on each spot, like maximum 5 milliseconds, because it's a scanning technique. So we don't illuminate the same area for very long. And about the radicals, we actually always measure with the flow. So hoping that the liquid flow can kind of refresh the liquid fast enough.
And what is the special resolution? So how much are you able to resolve this interface?
So the spatial resolution with the stick SEM for now, it's I would say around 30 nanometer in liquid. And there have been like now so a lot of development in tychography. So also measurement mode where we can go down to lower than 10 nanometer, but it's much harder to do there in a liquid environment for now. But yeah, this is basically the limits would be below 10 nanometer.
Okay, thank you.
Thank you. Adrian, you have the last question, please.
Hi, thank you. It was a really good talk. Thank you.
Thank you.
Yeah, my question. I mean, I've done lots of stick SEM on carbon systems, and as well as lots of other carbon spectroscopy, and beam damage is always a problem. I was just wondering if you know what the local temperature of where the beam is hitting. I don't know how you would know that, but I mean, it can change the structure. It can change how things are interacting, of course.
Yeah. So honestly, no idea about the local temperature, but maybe you realize that I focused on examples on kind of very hard carbon, so diamond, and this mesoporous carbon is also a very hard carbon, and it's mostly graphitic. So it's very different from polymeric or really organic molecules that would be much more sensitive to beam damage. I agree that yeah, if we start looking at polymers, then it will be much harder to image than diamonds, particularly, I believe, and mesoporous carbon. So I cannot tell you, any estimation we have for now. Where we try to estimate beam damage is just by scanning the same area multiple times, and when we don't see any change for 10 spectra or even a few hours, this is what we did for the titanium carbide, for example. Then we believe that it's quite safe from sample damage.
How fast can you measure a single spectrum? If you answered this already, I'm sorry.
So single spectrum, so the beamline is not super fast. It's maybe like 10-15 minutes if we average over a spot. And if we to take an image, it may be 2-3 minutes. So if we really want to have these images with high pixel resolution and high spectral resolution, this takes time. But again, when we scan, we don't stay on the same pixel for a long time.
All right. Thank you.
All right. With that, we should all thank Tristan again. I'll stop the recording